Welcome to Robotics 1. So, we are talking about the dynamics. So, robot dynamics. And to solve a robot dynamics problem, we are going to use the Lagrangian principle or Lagrangian equations, and that is given as L is equal to T minus V, where T stands for kinetic energy and V stands for potential energy. Now, the steps in working out the robot dynamics is step 1, draw kinematic diagram. Second, solve forward dynamic equation. Forward kinematics. And find out the Px, Py, Pz of the end effector or masses. Then find velocities, is d by dt of Px, d by dt of Py, and d by dt of Pz. Now imagine you have to find out the displacements or the positions of all the masses. So for an example, if your robot arm has mass m1 and the robot arm has mass m2, so you have to find out px1, py1, pz1. If you have mass m2, then px2, py2, pz2. And after that, you want to find out the velocities, which means you will take the time derivative of those terms, and then you will have to find out px dot, py dot, pz dot, px2 dot, py2 dot, pz2 dot. So you have to find out the velocities. Then once you find the velocities, you will have to find out the kinetic energies. So kinetic energy. And please understand there are two types of kinetic energies. One is the kinetic energy of translation. Energy of translation. And second is kinetic energy of rotation. So you have to find out the total kinetic energy. So which is kinetic energy of translation plus kinetic energy of rotation. Next step is you want to find out the potential energy. And potential energy you will find for each and every mass is given as mgh. So if you have m1, if you have two masses m1 and m2, so you will find out m1 gh1 and m2 gh2 if you have two masses. Then what you do is you find the Lagrangian, which is T minus V is kinetic energy minus potential energy, and then you can use MATLAB to solve the problem. Now, there are some variations to this. Let's start with a very simple problem, and then gradually we'll make these problems more and more complicated. So imagine the first problem that I'm going to solve is you have a revolute joint, and this revolute joint is attached to this revolute joint, and let's assume that there is mass m1 and there is mass m2, and we have done the forward kinematics for this. Step number 1 is to assign the coordinate system. So for 0th frame, 1st frame, and 2nd frame. So this is going to be the 0th frame, 1st frame, and 2nd frame. I'm going to call this distance A1. I'm going to call this distance L1. I'm going to call this distance E2. And I'm going to call this distance L2. And if you remember, this is my theta 1. This is my theta 2. So I have two angles, theta 1 and theta 2. And we spent a lot of time performing the forward kinematics on this. If you look from top, you would observe that this is like a double pendulum. This robot arm is like a double pendulum. L1, this angle is theta 1, and this angle is theta 2. This is mass m1. This is mass m2. So what I want to do is, if you remember, we performed the forward kinematics. We find out the homogeneous transformation. So we find out 0 h1. We find out 1 h2. And finally, we find out 0 h2. Everyone with me so far? So now what I want to do is, I want to find out the positions of mass m1. So I'm going to call this px1, py1, pz1. And I want to find out the positions of mass x2, px2, py2, pz2. So if you recollect, and we have solved this problem multiple times, the last column in the homogeneous transformation would give us their respective displacement. So I can say px1 is going to be L1 cosine theta 1, py1 is going to be L1 sine theta 1, pz1 is going to be A1. Are you with me so far? Then px2 is going to be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. py2 is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2, and pv2 is going to be A1 plus B2. A1 plus. Now what needs to happen is once we find out the Px, Py, Pz, I want to find out the kinetic energy. For that, I need to find out the velocity. So I need to find out Vx1, which is d by dt of Px1. And L1 cosine theta 1 is nothing but L1 minus L1 sine theta 1 dot. Vy1 is d by dt Py1 is equal to L1 cosine theta 1 dot. Vz1 is equal to 0. Are you with me? Because A1 is a constant. Same thing, I'm going to do Vx2 is L1 cosine theta 1 will become L1 sine theta 1 dot minus plus this term. What I need to do is I need to take the derivative of this, which will become L2 cosine becomes minus sine theta 1 plus theta 2, and then I need to take the derivative of the term which is in between. So because please understand, you have this cosine theta 1 and plus theta 2, so I need to take the derivative of this. So cosine theta 1. So there are different ways of solving this. You can actually expand this and solve. And you have y2, which is L1 cosine theta 1 dot plus L2 cosine theta 1 plus theta 2 1 dot plus L2 cosine theta 1 theta 2 dot, and then P dot V2, which is nothing but V2 is equal to 0. Now we have to find out the kinetic energy for the first mass. Kinetic energy of mass M1 is 1/2 M1 V1 square, which is 1/2 M1 minus L1 sine theta 1 dot square plus L1 cosine theta 1 dot square. Kinetic energy of the second mass is 1/2 M2 V2 square, which is going to be 1/2 M2, and I have this the whole dx2 term, which is minus L1 sine theta 1 dot plus L2, this is minus L2 sine theta 1 plus theta 1 dot minus L2 sine theta 1 plus theta 2 dot. This square plus the term we have here is L1 cosine theta 1 dot plus L2 cosine theta 1 plus theta 2 theta 1 dot plus L2 cosine theta 1 plus theta 2 dot square. Now please understand, since this robot is in the horizontal plane, the potential energy is going to be zero. So potential energy is going to be zero. So Lagrangian is T minus V, which is kinetic energy M1 plus kinetic energy M2 minus 0. And from here, you can use the equation in MATLAB. So what I'm going to do is, now I'm going to move on to MATLAB, and then I will show you the expression how to solve this using MATLAB. I'm going to share my screen. I'm going to open MATLAB. And if you have downloaded the dynamic scripts, so basically RR Robot Dynamics, run this first, open this code, and let's go line by line through this code. Okay. So what we have is we have two symbolic variables and their derivatives. Theta 1 is the first angle, theta 1d is the derivative of the first angle, which is theta 1 dot, theta 2 dot. These are the angular displacements and angular velocities. The gravitational acceleration g I have given as 9.81. For the sake of discussion, I'm assuming mass m1 is equal to 0.1. I'm assuming mass m2 as 0.1. I'm assuming the length L1 is 0.1, length L2 is 0.2. And you can choose some non-zero values of A, but I'm just assuming my A values are very small or are almost zero, so that it becomes a planar pendulum. Now, kinetic energy is, let's first look at the kinetic energy of the first mass. Can you see it is minus L1 sine theta 1 dot square plus 1/2 m1 L cosine theta 1 multiplied by theta 1 dot square. So this is the velocity of the first mass. Square of the velocity in the x direction plus square of the velocity in y direction gives you the total kinetic energy. Yeah, in this particular problem, the rotational kinetic energy will not come in the picture because this is the point mass. If we have a slender rod, then we will have the rotational kinetic energy. Because if you think about, when does the rotation kinetic energy come in the picture? When you have the mass that is distributed, so in that case, you will have to consider the rotational kinetic energy. In this case, it would just be the translational kinetic energy. There won't be any rotational kinetic energy. And I'll work out the problem of rotational kinetic energy in next few problems. And for the second kinetic energy of the second mass, again, I have this equation, minus L1 sine theta 1 dot minus L2 sine theta 1 plus theta 2 theta 1 dot minus L2 sine theta 1 plus theta 2 dot square. And then what I have here is I have this expression. So
I have actually, if you look at the equation that we just derived, that long expression is coded over here. So I have the kinetic energy of the first mass, kinetic energy of the second mass. Now, since our robot is in horizontal plane, the potential energies are going to be zero. If the robot would have been in the vertical plane, for example, if you had a robot like this, first arm, second arm, so if the robot would have been like this, then you would have potential energies. But since the robot is in horizontal plane, your potential energies are same. There is no change in the potential energy. If the robot arm was in vertical plane, then you would have change in the potential energy. So you would have this here, you will have 0 here. Now, if you look at the Lagrangian, L is equal to T1 plus T2 minus V1 plus V2. Then you have the states here, you have the internal forces, you have the external forces, and what you do is you run this code and then you will get the solution. So again, use Euler-Lagrange equation, the code, and again, since there are four states, theta 1 dot, theta 2 dot, you need to supply 4 initial conditions and then perform the numerical integration and you'll get the solution. So when you run this code, and please understand this robot arm is a simple 2 degree of freedom robot arm. Run this code and at the end it will generate the plots. First time it will take some time to run, but afterwards it will be okay. Please run this code. Yeah. And you will see, you should see result like this. So when you run this code, you are gonna get, we'll run this again. For some reason, my MATLAB is slow today. But I would encourage you to run this code and get the results. So this gives you the displacement and velocities. So plot 1, plot 2, plot 3, and plot 4. So we are going to follow the exact same process to analyze different types of problems. Let me take the second problem. Any questions here? Yeah. We are going to simple frame back to the state. So it would be particular robot. Since the value of x is not going to just go to V1 and V2 and put a shift in how would it affect say the value of the mass? The mass is zero, the mass will not be affected. Because at the end of the day, even if you shift the frame, what you are interested in finding, you are interested in finding the distance of the mass from the inertial frame. Even though you shift the frame, you are not shifting the mass. So that doesn't matter. So you will solve forward kinematics exactly the way we are solving. But finally, once you get Px, Py, Pz's for all the masses, take the derivative and solve the problem. So you don't take the shifting consideration. Yeah, mass is not going to change. Like even if we yeah. So let me take an example, and that would make things clear. So next problem.
I want to take problem number 2. Imagine now I have a robot. This is the revolute joint, and at the end here there is a prismatic joint. So if you want to take a look at this, so I would have, this is called as the revolute joint R, and this is the prismatic joint. This is my first frame, and again this is my second frame. So what I'm going to do is, we worked out this problem, but if you look at this problem from top, so if you were to look at this problem from top, you would observe this problem is something like this. You have a revolute joint, and you have a prismatic joint. A revolute joint, you have prismatic joint. So this, if I'm going to say this is mass M1, if this is so length L1, and I'm going to call this length L2. What I want to do is, this actually has 2 degrees of freedom. So one is this theta, and the next one is maybe this L1, or I would call this E. So we have theta and we have E. So what we want to do is, we want to find out the position of the mass, and the position of the mass is going to be, so I'm going to call this Px, Py, and Pz. So Px is going to be, so A1 plus L2 cosine of theta 1. Py is going to be A1 plus L2 sine theta 1, and Pz is 0. So what I need to do is to find the kinetic energy. So actually, let me write this simply. So I need to find out the kinetic energy. I'm gonna have a kinetic energy of translation, plus I would have a kinetic energy of rotation, and here are some cases possible. So for example, you have this first joint. If this joint has some mass, then you will have to take into account the kinetic energy of rotation of the first mass, kinetic energy of translation of the first mass. Since there is this mass in N2, which I'm calling N1, that's only mass, you have to take into account the kinetic energy of translation and kinetic energy of rotation. So to solve this problem, you have to follow the exact same procedure as we discussed here. So this is my 0th frame, this is my first frame, and this is my second frame, and say I have mass over here. And I would actually find out the homogeneous transformations. I would find out all the displacements, and then take the derivative of those displacements, and then find out the total kinetic energy, and I will find out the total potential energy, and finally you find the Lagrangian as kinetic energy minus potential energy. So I have kinetic energy minus potential energy. Please understand, we have solved this problem in the class. The only difference here is the robot would physically look like this. The robot would physically look like this. But if you want to represent the kinematic diagram of this robot, please understand there is a revolute joint and there is a prismatic joint. So you have this revolute joint and you have this prismatic joint. Step 1 is draw the coordinate space, solve the forward kinematics problem, find out the position of mass. For example, this is just mass at the end. Find the positions of the mass. Find the derivatives of positions, nothing but velocities of the mass, and then find the kinetic energy. Now, in this particular case, I want you to understand the way I have drawn this and the way it is shown here. This is the two-dimensional representation of this three-dimensional system. So as if you are looking from top, That's why you will see when you look from top, you will see the revolute joint and the prismatic joint. So if you want to solve this problem using MATLAB, now let me take you back to MATLAB. If you go to MATLAB, you will say RP. So RP, yeah. So you will see, actually, this is not the problem that I want to solve. So okay. So now here we have this revolute joint and then the prismatic joint, and the states are the first angle is theta1, the derivative of the angle which is theta1 dot. I have the displacement d2 and I have the derivative of the displacement d2d. The gravitational constant, I'm assuming it to be 1. Then I'm assuming the mass is equal to 1. I'm assuming the length is equal to 1. And since this is a slender rod, I'm considering Ix1 is equal to 0, Iy1 is equal to 0, Iz1 is equal to 0. Now, one thing I want to tell you is for this first problem, I'm going to treat everything is equal to 0. I'm going to assume my first mass is massless. I'm going to assume all the mass is located at the end. So I want you to make this change real quick. So what it means is the first mass, the first link is massless, and the entire mass of the robot is concentrated at the end effector. Then what I do is I find out the velocity of the Vx1, Vy1, Vz1, omega x1, omega y1, omega z1 is the theta1d. Then I find out the kinetic energy of translation. Please understand, since my Ix1 is 0, since my Iy1 is 0, since my Iz1 is 0, the kinetic energy of rotation for this system is going to be 0. So this is actually 0. So in this particular case, what I want to show you is you have, you see my screen, what you have is you have this revolute joint and on this revolute joint there is this prismatic joint and all the mass is located here. This is massless. This is massless. And the only mass, which is M2, is equal to 1 kilogram, is located here. That's why we don't have, if you look at this problem, and we will modify this problem when we will assume masses. So I want you to understand the first value, the L1, which is the length of the revolute, this distance L1, this distance is given M1. Background is good. Okay, yeah, sorry about that. So let me. Okay. Can you see my background? Are you able to see my background? Okay. So what you can see here is this is theta 1 dot, then D, D2 and D2. So these are the 4 variables. Now, if you look at first mass, everything is 0. So I can actually consider this mass M1 to be 0. And we are going to modify this script to include the non-zero masses. Mass M2, which is 1 kilogram. This is not a slender rod. So basically all the masses are attached at the end effector. And then what you do is you find out Vx1, Vy1, then you find out the kinetic energy of translation, you find the kinetic energy of rotation. Then what you do is you go on to the next part, Vx2, which is the kinetic energy of the translation for the second mass, kinetic energy of, so for first mass, since there is nothing, this will be 0. So the only thing that will be left is for the second mass. And then what you do is you sum the kinetic energy of translation, kinetic energy of rotation, and then actually, so basically I made this problem a little bit more complicated than it needs to be. But the idea is, once you find out the kinetic energy of this mass, you use the Lagrangian. L is equal to T minus V and use the MATLAB to solve the problem. So this problem would actually look like something like this. This problem would go away. This would go away. This, it will be just V2. So Vx1, Vy1. And then will go away. And then what you do is you basically solve this problem. 1, 2, 3, and 4 in this code. and then you will get the answer.
Dr. Mukher,
Yeah,
you have to, I mean, to like use dynamics, right?
yeah,
We need to solve power kinematics. So that is necessary.
yeah.
Yes.
So forward kinematics is a necessary step. So what that means is everyone remembers forward kinematics, right? Okay. So what that means is, just let me know if this is a little bit fast. I will put in what it means. I didn't solve the forward kinematics for this because if I remember correctly, we solved this problem in forward kinematics. So what needs to happen is you will have A1, then you will have A2, and you will have to find out 0H1, 1H2, and 0H1 and 1H2, 0, 1, 2, and then find out 0H2. And in 0H2, you are gonna have Px, Py, Pz, right? You grab this Px, Py, and Pz. Take the derivative of Px is going to be Vx. Py d by dt of Py and Vz is d by dt of Pg.
Oh, so forward kinematics is to get the Px, Py, Pz, so you differentiate.
Yes, and forward kinematics, I actually, what I did here is I took the shortcut. And the reason I took the shortcut because I believe that this problem we already solved. So we have the solution, but the step is we have to do the forward kinematics, get the values of Px, Py, Pz, find Vx, Vy, Vz, and then find out the kinetic energy as 1/2 m2 Vx square plus Vy square plus Vz square.
So here we get zero displacement.
And in this particular case, now if you look at this robot arm is in the horizontal plane, which means the potential energy is going to be 0. Yeah.
So if you, it's not necessary that the position of the mass be at the end of the link. So even though it is the position of the mass is the function of a system variable, it's not necessary that it is in the homogeneous transformation. For example, if the mass is in the middle of the link, it will not be an homogeneous transformation there.
Correct. So we haven't looked at those problems. So what we have seen, and that problem will come next. So for an example, see, instead of mass being over here, say mass is over here. Then what do? So when you do the homogeneous transformation, you just consider that length to be this length. And I will work out these problems. So the idea is you find out the mass, find out its Px, Py, Pz, find out the velocities, find the kinetic energy, find the potential energy, then find the Lagrangian, which is kinetic energy minus potential energy.
For this example, like we have to shift the frame backwards, right, Professor? Because the value of x is not going to intersect z.
Correct.
So we get zero displacement. If I differentiate, I will not have any velocity.
No. So at the end of the day, you will have to find out the homogeneous transformation and the forward kinematics of this mass. Let me tell you what is exactly happening. So as you can see, if you remember, the 4 rules or 3 rules won't be satisfied. So what needs to happen is you will have to shift the frame back. When you shift the frame back, what's going to happen? The 0th frame
and the shifted frame will coincide on top of each other. But what that means is the total length where the mass is going to be A2 plus D2. Are you with me? And exactly that is what is happening here. For example, here you see that A1, so here this is A1. This guy, this gets added with this guy and multiplied by the cosine theta. That exactly what happens.
In this case, I don't think true is duality. Right. Yeah, no, it is, if it's in the vertical plane.
So if you really want to see what's going to happen, we will have to assign the coordinate frames, go through the homogeneous transformation, but at the end of the day, this is what is going to happen. You are gonna have this distance A1, this distance plus this distance which is L2. And when you take a look at this total distance is nothing but this radius, it will have its cosine component and it will have its sine component. Everyone understood?
But in this case, I don't think it is true is duality. It's bounded in the vertical plane. Because, no,
Okay,
I'm not sure.
all right. Let's start. So this is C0, X0, Y0, right? This is C1. Now X1 has to be perpendicular to X0. No matter what you do, the rule is gonna get violated. So because what you do is X1 has to be perpendicular to X0. So basically X1, so you got the Z1, X1, and Y1. You got Z2, Y2. Now I want you to notice that this is your X1 and this is your X1. So they are not intersecting. So that's why what you will have to do is you will have to shift it and then solve the problem. So at the end of the day, what's gonna happen is you are gonna get an equation with something like this. So when you go to your MATLAB code,
N minus one, right? If it's made by a sense of P, so it is not intersecting. If we assign something on top of that, this is the net. Now the second coordinate is like this. So this X is now going to intersect with this one. This is the direct here. Because there is a shift of E1.
okay. So you want me to solve this problem completely? Be happy to solve the Okay, I got the solution right here. Sorry. I got the solution right here. So I did not solve this because I believe that we have actually worked out this problem in the past. Only thing what we didn't do is we didn't formulate the Lagrangian equation.
I think maybe not all of you are experienced with it. So from next student might not be able to see this.
Oh. It is not visible here.
Okay. So these are the steps: draw kinematic diagram, identify masses, forward kinematics analysis, find the kinetic energy of each mass, find the potential energy of each mass, and then total kinetic energy, total potential energy, find LT minus V, and use MATLAB to solve this problem. Now, in this particular problem, what I did is I did the simplification. So the first, and we are going to make this problem more complicated. So right now, the only thing I'm assuming n1 is equal to 0, n2 is equal to 0, and there is a non-zero value of n2. Everything else is 0. All the mass is located at the end. And what you do is, when you find out the displacements, so this is your first coordinate frame, this is your second, zeroth coordinate frame, first coordinate frame, and second coordinate frame. All the mass is located over here. And what I did is I actually performed the forward kinematic analysis and found out the displacement of the position of the first mass, position of the second mass, and position of the third mass. But this problem, I'm ignoring all the masses, only I'm keeping the last mass. And then what happens is, what you can do is, the only equation that you should be focused on is the equation for this mass M3, which is T2 plus L2 by 2. My sign convention, I used different terminologies, but at the end of the day, what you have is, you have the equations for the masses. And here, I want you to take a look at it. You have the kinetic energy for the third mass and the potential energy of the third mass. And then what you do is, you add the kinetic energies, subtract the potential energies, get the Lagrangian, and solve the problem. So everyone understood this? Let me. So what you have is, you have just this mass M1. So I'm gonna write this down on the board. Px. So it is x. This is y. Px is equal to, I'm gonna call this, say from here to here, I will call this D2, and from here to here, I'm gonna call L1. So this is going to be Px is D2 plus L1 cosine theta 1. Py is equal to D2 plus L1 sine theta 1. Pz is equal to 0. Now I need to find out the kinetic energy of this mass. So d by dt of Px. Now please understand, d2 is a function of time, cosine theta is also a function of time. So this equation is d by dt d2 cosine theta 1 plus L1 cosine theta 1. Now I want you to notice, d2 is a function of time, cosine theta is a function of time. So I need to get d2 minus sine theta 1 dot plus d2 dot cosine theta 1 plus L1 is a constant, L1 sine theta 1 dot. Are you with me? Okay. Now next part is d by dt of Py. Same thing, d by dt d2 sine theta 1 plus L1 sine theta 1. D by dt, same thing. D2 is a function of time, sine theta is a function of time. D2 dot sine theta 1 plus D2 cosine theta 1 dot plus L1 cosine theta 1 dot. So this is Vx, this is Vy. So I have Vx and I have Vy. Now what I need to do is I need to find out the total kinetic energy. Total kinetic energy is going to be 1/2 m2, basically this guy Vx square plus Vy square. Now here I'm assuming gravitational acceleration is like this. So this is the total kinetic energy. The potential energy is going up, which is this distance, which is d2 plus L1 sine theta 1 plus d2 plus L1 sine theta 1 mgh. So potential energy is going to be mg and this is h. Are you with me so far? The Lagrangian is going to be T minus B. So this is T and this is V.
So,
Yeah.
in the Vx, we are considering D2 as a constant length, right?
So no, D2 is the distance of this piston or this pendulum, this prismatic joint from the origin. So this is changing. L1 is the length of this piston. So L1 is constant, but D2 is changing. You see what I'm saying?
Yeah.
So basically what I'm saying here is this is the piston. This distance is constant, which is L1. And this distance is changing. So which is D2 as function of time. D2 is changing. Yes. L1 is constant. Okay.
Yeah, I guess in this case, since there is no mass associated at that lane, so wouldn't it be easier if we consider the L1 as well? So, like,
No, L1. So hold on. So can you see if this piston goes down here,
yeah,
D2 is 0.
right,
If piston goes all the way over here, D2 is maximum. But I'm assuming this as L1 because L1 is, you can change, do whatever you want. That's totally fine. But so what I want to say is L1 is a constant and D2 is changing. Okay, so my online students, can you see this development?
someone just commented that the screen camera is too high.
Camera is too high.
Yeah.
Camera is too. Writing is off the screen. Okay. Now can you see my writing? Okay. And what I wanted to do is I wanted to actually implement this onto the code that I showed you. So let's try to implement this code. And start with me. The first thing is symbolic variable theta 1 d, d2 d2d, g is equal to 9.81. There is nothing here. So all the masses are 0. All the masses are 0. And what I'm going to do is so I have I'm going to call this m2 is equal to 1. I will
Ignore everything. So let's program this. So what I need to do is I need to find out the Vx. Vx is equal to minus d2 multiplied by sine, okay, theta 1, theta 1d, right? Yeah. Okay, then plus no d2d multi d cosine theta 1 minus L1. So I need to specify what L1 is. L1 is equal to 1. L1 sine theta 1 theta 1d. Okay. Vy is equal to, okay, d2d, right? Multiplied by sine theta 1 no d2 no, sorry, not d2d, just d2. d2d sine theta 1, okay, sorry, sine theta 1 plus d2 times cosine theta 1 theta 1d. Okay. Are you with me so far? So this is, now I need to find out the kinetic energy. Kinetic energy is equal to 1/2 times, so I'm gonna call this M2 here. M2 multiplied by Vx square plus Vy square. Are you with me so far? The potential energy is equal to, this is my datum. So this is at the distance d2 plus L1, d2 plus L1 sine theta 1. So and multiplied by M2. Are you with me so far?
Can you just explain again why we have rotational kinetic energy here?
Yes, I will explain this once again. So if you look at the velocity in x direction, and you look at the velocity in y direction, the total energy is 1/2 m vx square plus 1/2 m vy square. If you think about the rotation of rotational energy, it's given as 1/2 I time omega x square. But this is a point mass. This is not a slender rod. That's why basically the value of I for this guy is actually 0. Now we are gonna solve this problem later. Wherein what we will have is, we assume it to be a slender rod. And when we assume it to be slender rod, we will have something called as Ixx, Iyy, and we will have Izz. And at that time, we will have the rotational kinetic energy Ixx omega x square multiplied by half, Iyy omega y square multiplied by half, Izz omega z square multiplied by half. But since this is the point mass, it only has the translational energy.
Also, Professor, like, here also, once we look at the top view, the arm is in horizontal plane.
Correct.
Then why is not the?
Yeah, you are absolutely right. In this particular problem, the way I have drawn this, the way I have drawn it, this looks in the vertical plane. If the robot would have been something like this, the robot would have been something like this. Then the potential energy would be zero.
Okay.
But what I have, the way I have drawn this, I have drawn robot
Yeah.
to be something like this,
Oh, yes.
right?
Got it.
So that's why. That's why I have find out. Yeah.
But yes, and when the frame is given, and it seems like it's in vertical plane, so what do we,
So frame is, I don't remember. The frame is given like this.
no, the coordinate frames, what the origin, the first inertial frame, it's like the Z is coming out, so it's like in a vertical plane.
So. So one
Yes,
thing,
exactly like that, the Z
Yes.
is coming outside, right?
Z comes out,
he comes out.
Z comes out X, Y.
Yeah, so
It seems it's like in a vertical plane, so what do we have?
so basically solve like this.
So do we consider it the horizontal plane or vertical?
It's totally up to you. You can define. A robot could be in the horizontal plane, or robot could be in the vertical plane. It doesn't matter. So just state your assumption. You are assuming the robot in the horizontal plane, or you are assuming the robot in the vertical plane, and solve the problem. You won't lose any points because it's just a representation of the robot. If you look from robot from top, it would look like this, but it still be in the horizontal plane. If you look from the side, if the robot is in the vertical plane, just write your assumption and solve the problem. That will be fine.
Because, like in the previous example, what we discussed, when the robot was actually in the horizontal plane, there was a vertical distance from the inertial point and the end effect.
Correct.
So why does not that particular height, that is the height difference? Obviously, once we look at from the entire thing from the top, it is going to look in the same plane. But if we look from the front view or the side view, it is going to have a displacement. And why do we not calculate that particular?
So now let me answer your question. Actually, this is a good question that you asked me. I will try to answer this question. So potential energy is with respect to a reference. Now, whether you consider your reference at the 0th frame or whether you consider your reference at the 2nd frame, it's just for the reference. Even if you consider even if you consider Z, remember in Lagrangian equation, we are going to take the derivatives. So that constant term, when you take the derivative, is going to become 0. So in other words, what I'm trying to say is, if the height is not changing, when you include that in the Lagrangian equation, that term will vanish. Everyone understood this? Once again, I explain. So the question was, and that's a very valid question. So the question is, imagine that you have this say robot. If you consider this as a datum, this mass is at a non-zero value of h. So there is some h over here. So why not to consider that? You can consider that, that is totally fine. what's gonna happen is when you take the derivative, since this potential energy is going to be a constant term, when you take the derivative, it will become zero. Unless this mass is going up and down, which means its potential energy is changing, it won't be in the picture. Alternatively, what I can say is, I am assuming my datum over here. But that's okay, you can actually, so now I want you to look here, potential energy got this over here. So now I need to use the Lagrangian is equal to kinetic energy minus potential energy. And assuming I did everything correctly, or did I make both? Yeah, I made a mistake. You're right. Of course. I forgot to multiply by G, right? That's what you're saying, right? Okay, good. So. And then at the end, you will get.
Sir, I was also getting something similar to this, but my question is, the distance goes all the way to 600, and I don't think that's the limit of our prismatic body.
So. To be honest with you, we did not specify the length of the prismatic line. We did not adjust. It also depends upon the initial condition. So if your initial conditions are very small, so and again you will notice that this robot arm, the way we have drawn this, what is happening is you have this robot arm and you are spinning this. So because of the spin, what's going to happen is that there will be a centrifugal force that will go out. So that is what is happening. This is uncontrolled motion of the robot arm. So what we will do is, next part is, we are going to assign masses to different lengths, and we are going to solve a 3D kinematics problem from start to end, starting with homogeneous transformation. So in today's problem, what I did, we already solved the homogeneous transformation. We already have Px, Py, Pz. We just did Px dot, Py dot, Pz dot, and use the Lagrangian equation. Next class, we are going to look at a problem start to end, starting from the homogeneous transformation, getting the answers, finding the kinetic energy, potential energy, and solving the dynamical equation solution. So we will actually go from start to end. But if you want, here is the code. For my own satisfaction, I will explain this code once again. There is theta1 d, d2, d2d, length is L1, mass M2 is 1, and gravitational acceleration is 9.81. Please understand, everything else is massless. The end effector mass is significantly larger than the mass of the links and mass of the attachment. We found the positions of the end effector. We found out the velocities of the end effector. We found out the kinetic energy. We found out the potential energy. And then we did Lagrangian as kinetic energy minus potential energy. And then we used MATLAB to solve the problem. And then this is the answer that we got. Everyone understood this question? Yeah.
If we do assume there is a mass shift of M1, so in our question we consider it as zero. But if I have a mass of M1 exactly at this point, when I do the shift, I get a displacement of 0, 0, 0. When I look at frame 1 with respect to 0. So then what happens? I'm really sorry.
No, I understand.
Make sure that I really understand this problem.
Yeah, no, I will solve that problem. Trust me. I will actually solve that problem. But so currently what I'm assuming is all the mass is located at the end. Now the question is, what happens if I have a mass somewhere here? Okay. So when we are solving the homogeneous transformation, we are actually not trying to find the position of this mass. But if our mass is somewhere here, we need to know the Px, Py and Pz of this mass. So what that means is when we are going to solve the homogeneous transformation, rather than taking this length as L, I will take this L by 2. And that will give me Px at this mass M1, Py at this mass M1, and then Z, Pz at that end. I will work that problem out.
So here, if you look at this prescribed design, right?
Yeah.
Basically you are shifting. So in my assumption, I'm saying M1 is located exactly where this coordinate frame.
Correct.
When I shift, what happens?
M1 will stay there.
It will not.
Mass will not, only coordinate frame changes. Mass does not change.
So when I will only look at PH, Py, Pc.
Correct.
And so like even if I get a displacement vector of 0, 0, 0, because I shifted the frame.
Yes. The next frame you will get it actually, you will, when you transform this, you will actually get non-zero values of this place. I will solve this problem. We are not done with dynamics. Please try to understand. We are studying three-dimensional multi-body dynamics. If you understand this, you can solve any dynamics problem, whether it's celestial mechanics, celestial dynamics, or quantum dynamics. Everywhere, Lagrangian principle, the energy principles are omnipresent. Energy principles are universal governing principles. So Lagrangian approach and Hamiltonian approach will always work. Newton's approach, then you have relativistic corrections, but here nothing. So again, if it seems like a little bit confusing, that's okay. I'm gonna explain. Next 2 or 3 lessons will only be focused on dynamics. I'm going to solve again 5 to 6 more problems. And I promise you at the end of those 5, 6 problems, you will master this concept. At the end of the day, this is what we are going to do. Find the kinetic energy, find potential energy. The only thing is, in this particular problem, we are looking at the point mass. We are not looking at the distributed mass. We are not looking at slender rod. That's why we are not looking at kinetic energy. Because kinetic energy of rotation. Because if you have a point mass, even the point mass is rotating, since the mass is located at that point, the radius of gyration is 0, which means the total kinetic energy of rotation is 0. But that's why in this particular problem, we are ignoring the kinetic energy of rotation. But in next few problems, we will actually consider the mass that is distributed, and then you will notice that there will be kinetic energy of translation and there will be kinetic energy of rotation.
So for real robot, the mass is based on the center of mass of the interior wings, right?
So we always derive the equations at the center of mass because the moment of inertias are easy. What happens is, we'll talk about it in next class. If you have a 3-dimensional object, you have something called as 3x3 inertial tensor. As long as you consider the centroid, the off diagonal terms of that inertial tensor will become 0 and your problem becomes very simple. And actually, I will take few examples and I will actually show you how that problem simplifies. So bear with me. And I have actually changed the due dates for all the assignments. So if some of this material, I think to the best of my knowledge, I postponed all the assignments that are dependent on the material on dynamics. But if not, let me know and I will change the due dates. But first we need to finish this, only then you will understand how to solve the dynamics problem. Okay, with that, I'm gonna stop.